This is the brief on spherical divergence. All right, let's talk about divergence. It's really just how we measure a flow, like heat or a fluid spreading out from a point. But what happens when you do this on a sphere, like a planet? Well, that's where the math gets interesting, and we're going to break it down. First, it really all comes down to geometry. On a sphere, the surface area isn't uniform like it is on, say, a cube. Just picture the North Pole. The area there basically shrinks down to nothing. So the formula has to correct for this. That's why you'll see factors like r squared and sine theta tucked inside the derivatives. They prevent the math from miscalculating the flow where the surface gets all pinched. Second, this geometry directly shapes the final formula. The total divergence is built from three parts, for the three ways a flow can move. Radially, so in and out; polar, that's up and down; and azimuthally, which is just around. And those geometric correction factors? They're woven right into the math for each velocity component, making sure the calculation perfectly matches reality at every single point. Finally, how do we know all this complex stuff is actually right? Well, it's confirmed through some seriously rigorous proof using tensor calculus. See, physicists need formulas that work no matter how you orient your coordinates. This framework guarantees that our solution, which started from physical intuition, is mathematically sound and works universally. So, the complexity of spherical divergence is rooted in geometry, and its consistency is proven through tensors.